Okay, good afternoon. So this is the fourth, sessions of tutorials on the DC systems. It is a repeating of this morning's session. And so today we would like to talk about one more ring circuits, which is about the cable sizings. Okay, so before we start talking about these examples, we found that they still have many students who have problems on understanding the voltage drops on the cables. They're sometimes very confused with the cables, circuits, and conductors. And so therefore here I would like to draw one example showing you the meanings of the cable voltage drops. So suppose then we have a source here. So the source, positive side, negative side. Generally, we can use a non-cable. This cable may be single core cable or two core cables. For examples, we have a core cable that have two cores like this. At the end, it connected to the load. So this is the cables, right? This is cables. This is cables sheath, right? For example, it had the cables sheath. This cables sheath. Sheath. Okay, this is the cables sheath. Okay, it's cables sheath. Okay, so suppose the source has a voltage E. Then to the load, it has the voltage V. Okay, so the conductor has a resistance. Then you will have currents flow on the cables. So you have current flows on the cables, which in this way, in this way, in this way, in this way. Okay, so suppose that the load has an equivalent resistance R, and the cable, one core, has a resistance R, cable. So this is R cable. And the current here is I. Current here is I. Then, as you're looking at this, this circuit, this is the source which has a voltage E, and we're using a cable which is two core cables. One core connected to the positive polarity of the source. The other core connected to the negative polarity of the source. The load is connected between the two conductors at the remote side of the cables. The cable has a length. The cable has a total resistance RC. So how to calculate total resistance? If you know the per meters values, then you can calculate. So then the source voltage equal to the voltage to the load equal to E minus 2 times the I times the RC. RC. And or E equal to V plus 2 times the currents on the cable. This is current on cable times the one core cables. One core resistance of the cable. The 2 here means two cores. If you use in the Kirchhoff, if you use in the Kirchhoff, right, voltage low, so this is up, this is a voltage down, this is a voltage drop, this is a voltage drop, voltage drop. So up, drop, drop, and drop. So that's this equation, right? That's the equation. Or we say up minus the one conductors times RC minus the E minus the I times RC equal to 0. Equal to 0. That's the relationship. Here, the voltage drop on cable equal to 2 times the I times the RC. So RC is 1 core resistance. In general, the cable values is the voltage drop per ampere per meter for 2 conductors. Okay. Okay. So this is the relationship where we're looking at, right, such a circuit to see the source voltage, the cables. Okay, so the cable resistance, one core resistance, another core resistance, current on one core, current on another core, right? Opposite to each other, and the load. The load has resistance R, load has current I, and load has a voltage V. Okay, their relationship. Okay, the loading voltage equal to the source voltage minus the voltage drops on the cables. Or we say the source voltage, right, minus the one core voltage drop minus the load voltage drop minus another core voltage drop. That's zero. So anyway, that's the relationship, okay, in general between them. Okay, so the voltage drops on the cables here, as you can see, that is the 2 times the current, okay, on one core times the RC. That is the one core resistance. So the RC is one core resistance. Okay. Now, on the other side, okay, so in general, we have the tables. The table values is the voltage drops per ampere per meter for 2 conductors in millivolts. Okay, remember that's the difference. Okay, in general, the table values is the voltage drops per ampere per meter for 2 conductors in millivolts. Okay, therefore, okay, so what does it mean? What does it mean? So, cables total voltage drops. Okay, tables total voltage drops. So the total voltage drop on a 2-core cable equal to the length times the current cable length times the cable currents times the voltage drop per ampere per meter, okay, per meter. Okay, because this already has 2 conductors, per meter, okay, or 2 conductor. Okay, now one core total resistance equal to the one core equal to the cable length times the voltage drops per ampere per meter, and divided by factor 2. Okay, so here is some points. Okay, so have a look at this, right? Okay, diagrams. Try to understand, okay, the meanings of voltage drops, the relationships between the source voltage, the voltage drops on the cables, okay, and the voltage to the load. Okay, so their relationships. Okay. Now here, if you're using the table values to estimate the voltage drops, okay, so then you should understand the meanings of the values in the tables. So the table value is the voltage drop per ampere per meter for two conductors in millivolts. So the total voltage drops on a two-core cable equal to the cable length times the cable current times the table values, which is for two conductors, okay? Time table values. No factor, already be two conductors. And one core total resistance is the cable length, okay, times the voltage drop per ampere per meter from the table values divided by factor 2. Okay, because this voltage drop per ampere per meter in the table is for two conductors. So you divide it by 2 is the one core total resistance. Okay, that's the logics between the cable's voltage drop per ampere per meter for two conductors and the per core's resistance values. Okay, I think, right, I explained, okay, clearly that the meanings of the cable voltage drops. Hope no students confuse it again. Then we back to these examples, so looking at the question itself. Okay, so do you still have any questions on the issues of the voltage drops, cable voltage drops? Okay, if you still have, you can write down immediately. Okay. Okay, now we're looking at this question itself. It says that a two-core cables, just like this, right? A two-core cables is to be used as a ring circuit, okay? Distribution cable to supply loads from a 200 volts DC source. So there are several loads which listed in the next slide tables, okay? Okay, so we have a ring circuit, so which using a two-core cables, okay, supply powers to different loads and different positions, okay, from a 200 volts load source. Now, determine the size of the cable, okay, so that the voltage drops from the cable to any source, any load, okay, in the circuit to be within 2.5% of supply voltage. Okay, so we have several loads that you should choose cables so that the cable voltage drop per ampere per meter is small enough so that the total voltage drops from the source to any loads in the circuit smaller than 5%, right? 2.5% of the source voltage. That's the meaning of it. Now, as I said, that the cable voltage drops depends on, okay, the temperatures, depends on the installation, okay, methods. So different methods result in different, right, voltage drop per ampere per meters. Okay. So here, so telling you the situation, assuming that the cables is running a cable trench and clipped direct. So this is one installation method of cables. And assuming that the ambient temperature is 30 degrees. Okay, then this cable will be used in such a way. Okay, so this is question itself. Actually, in the previous sessions, already telling you that in Hong Kong, we have basic requirements on the voltage drops on the systems. Okay, so that's it. That's the for source, the total voltage drops, okay, no more than 6%. Okay, for the distribution circuit, that the main circuit, okay, 2.5%, okay, and final circuit 1.5%. Okay. Okay, so we go ahead to see, okay, how many loads, okay, has been connected to this ring circuit. Okay, so it says that this ring circuit has 5 loads connected at different, okay, positions. The load A, which has a rating current, that means using current 20 amperes. Okay, this load, the current go through this load, okay, 20 amperes, located 150 meters away from the source. And load B with a rating current 50 amperes, located 200 meters away from load A. And load C, rating current 25 amperes, okay, located 250 meters away from the load B. And load D, rating current 40 amperes, located at the position 300 meters away from the load C. And finally, load E, which drawing 30 amperes from the source, located at 100 meters away from the load D and 10 meters away from the source from the other side. Okay, so from these tables, you can find out the load numbers and the ring circuit length of it. For good understandings of it, let's looking at the next slide, where I have drawn a simple circuit of it. So, okay, so now we looking at the ring circuit itself. So this ring circuit, the ring circuit is a two-core cables. So two-core cables, starting from so the source 200 volts source, we have a two-core cable. So this two-core cable, 150 meters away, we have load A, which drawing 20 amperes. Another 200 meters away, we have load B, which drawing 50 amperes. Another 250 meters away, we have load C, which drawing 25 amperes. And 300 meters away from load C, we have load D, that drawing 40 amperes. Another 100 meters away from D, which also 200 meters away from the source in another side, that drawing 30 amperes from the source. Okay, so for good understanding, let me add another call here again, to explain to you more clearly about the solutions here. As a matter of fact, we're using two core cables here. So suppose I expand this circuit into a two core circuit. So actually we have a source. So this is the positive side. This is the negative side. Okay. So then another core connected to the negative polarity. Okay. So we suppose that from the source to the load A, on the first part of cables, we have a current R1 in a direction like this. And on the second part of the cable from load A to B, we have a current I2 in these directions. And in the third part of cables, which is 250 meters long, between the load B and load C, have a current in this direction, I3. And on the other side, from the source, to the load E, 200 meters long, has a current in this direction. That is the I6. And between the load E and D, we suppose has a current I5. that has a current direction from the E towards D. Okay. On the cables between the D and C, there's a current, right, in the inner core, from the D to C, right, hence a current I4 in this direction. Remember current, right? Once you assume the current direction, so you suppose the current flows from high potential to low potential side. So when you write established equations, using these assumptions. Similarly, so for the part 1, you have I1 in the outside that is opposite, to what you assume in the inner side, and I2 here opposite, and I3 here opposite. And I4 opposite, and I5 opposite, and I6 opposite. Okay. For each part of the for each part of building, for each part of the cable, it has a resistance. So it has a resistance. This part of resistance. This part of resistance. Okay. You have resistance here. You have resistance here. Okay. You have resistance here. You also have the resistance here. You have resistance here for this part of a cable. You have resistance here. And similarly, you have resistance here. You have resistance here. The same. Okay. You have resistance here. You also have resistance here. Okay. For each load, although it is not given, but it has resistance, we say RE. It's not given, unknown. RB, right? So you also has, RC. You have RD. You have you can define this R1, R2, R3, R4, R5, and R6. It doesn't matter. So for general case, in general, for each branch it is assumed that the current flows from high potential to low potential side. Okay, so we have two general cases. In a circuit, not this circuit, right? In a circuit, for each branch of a circuit, you may assume a current direction and a symbol, okay? Using a symbol, say IN, okay, IN. That branch has a current IN, which has a current direction, assume it, okay? Then, okay, in the Kirchhoff current law, okay, you're using the assumed current with the assumed right symbols to establish the equations, saying that for each junction points, the current go in equal to the current out. Okay, that's the Kirchhoff current law for one junction points. Okay, then once you assume the current directions, you should also assume that the current flows from high potential to low potential side. Okay, so looking at the current direction, okay, suppose that the current flows from high position side to the lower potential side. Then, in such a way to establish the Kirchhoff voltage law. Okay, that's the meaning of it. Okay. Now, looking at these examples, we can establish the current relationship, okay, at different junction points. Looking at the junction points here, okay, junction points, these junction points, okay, looking at these junction points, we have a current R1 come in this point. We have a current I2 out this point. We have the current 20 amperes out from this point. Okay, the 20 amperes is the current on the load A. Current R1 is not the current on the load A. Okay, that's the difference. Okay, here the current on the load A is 20 amperes. Okay, so the current in these points, I1, out these points, I2 and IR, and 20 amperes. That's why we have the R1 equal to 20 amperes plus I2. That's the relationship, okay, looking at these points. Similarly, we've been looking at the points, okay, between I2 and I3. The I2 in this point, the I3 out this point, and 50 amperes, that is IB, out these points. So we have I2 equal to 50 plus I3. Okay, all this depends on how you assume the current directions. Once you assume it, do not change it. Okay, then for the point C, okay, then the current I3 is in, the current I4 is in, and current 25 amperes is out. Okay, this means that the load C, according to your assumptions here, the load C getting current from two sides. Okay, partially from I3, partially from I4, in total 25 amperes. So I3 plus I4 equal to 25 amperes. That's the meaning of it. Similarly, looking at the point D, okay, this point D, that's the I5 in, I4 out and 40 out. So I4, equal to I5 minus 40. The same things. So I5 minus 30 is I4. Or you say, I5 equal to I4 plus 40. The same. And looking at point E, you will find that the I5 out, 30 out, I6 in. So therefore, I5 equal to I6 in minus 30 out equal to I5 out. That's points. So similarly, one can, looking at the point at the A and outside, looking at the point and B outside, looking at the point C and outside, open and point D, outside, point E outside. You will got the same, right, equations. We got the same equations. So anyway, so you can find out the relationship between I1, I2, I3, I4, I5, and I6. Choosing 5 junction points, not repeat the junction points. Right, junction points and the different circuit, circuit positions. So you can do it in a different way. So it doesn't matter that you will got 5 equations. Not enough because we have 6 unknowns. 6 unknowns. So this is the Kirchhoff current law applying to 5 junction points. For each junction points, we got these equations. Do not combine 2 junction points together. You do not use an I1, I2, and I50. Do not use that. Some students may use an I1, I3, and 50. You cannot got that, right? Because that not continuous. The current here is not continuous, right? I1 and I2 not continuous. Now, then we can choose in one loop, not including the load. We choose in the inner loop. Because we use the same cables. We use the same cables with the same cores. So the resistance of the cores per meter per ampere is the same. Per meter per ampere is same. We assume the resistance per meter per ampere. So resistance per meter is is a value, say R or X. It doesn't matter. X. Then the total resistance along a given part of the cable is the resistance per meter times the length of the cable. And the voltage drop is the resistance per meter times the length and times the currents. So we're looking at this curve for the part A. Suppose the resistance per meter is R. Then the voltage drops on this part of cable is the 150 meters long times R1 times the resistance per meters. Plus, this is voltage drop, because we assume the current from high potential to low potential. So 150 meters with I1, you have voltage drops. And another 200 meters with I2 is another voltage drops. That is 200 meters long. I2 is the current, the second parts. And the third part, based on the directions of the current, you have further voltage drops, which is 250 meters long with I3, 250 meters long with I3 voltage drop. Now, the fourth parts here, which has 300 meters long, and with a current I4, but in direction that goes to C. So from the point C to point D, that is voltage up, because current goes from high to low, so current up. So that is minus in opposite to the previous 3. So that is voltage up 300 meters, I4. Similarly, okay, between D and E inner, okay, in clockwise direction, that is the 100 meters long and current I5 and voltage up. Okay, and the last part that with the current I6, okay, count in clockwise direction, that is 200 meters long, I6, okay, current, right, voltage up. Okay, so R1 drop, I2 drop, I3 drop, I4 up, I4, I5 up, I6 up. In total is 0. The R here, okay, is the resistance, okay, per meters values. Okay, per meter per conductor or two conductor doesn't matter. Okay. So the total voltage drops in one loops be 0. Because the resistance per meters is non-zero. So this part in the bracket part should be equal to 0. So we have 6 equations for 6 unknowns. Okay, then you can find out the solutions for R1, I2, I3, I4, I5, and I6. Similarly, you can choose the outright ring as a ring, okay, that the voltage drops, okay, the whole range has voltage drops be 0 in each directions, okay, If you choose, right, some students may, right, try to make things be, okay, different from the others. For example, okay, if you try to choose this right loop, okay, if you try to choose this loop, then what happened? So you have taken account, right, the I4, okay, with the 300 meters, that's what it dropped. And also, that is the 25 amperes go through RC, that is what it drops. Okay, and, right, I4 goes the outer side, right, that is what it drops. Okay, and also, okay, RD with 40 amperes, that's what it up. And what it up. Okay, so suppose this is one, okay, loop. This is loop 2. Okay, this is the one loop values. If someone, okay, using the loop 2, then what happened to it? The loop 2 will be the R is the per meter values times the 300 meters long. Okay, that is what it drop. Plus the 25 amperes times, okay, this is the 300 meters. Okay, this is the, okay, 25 amperes times the RC. This is what it drops. Plus, okay, another, okay, 300 meters, okay, times, okay, the I4, okay, minus, okay, that is the 40 amperes times the, okay, resistance of the RD equal to 0. This is using the loop, right? 2. Okay. So if you're using the loop 1, we got these equations. Okay, we have no more unknowns. If you got, right, using the loop 2, you have 2, right? You have, okay, one more unknowns. Okay, one more unknowns. times I4, right? Sorry. Okay. So if you're using the loop 2, you can establish equations based on current voltage law. That is the per meter's resistance 300 meter long with current I4. That's the voltage drops in the inner part of the that, and then 25 amperes go through the load C RC of the load C resistance plus 300 meters I4 right. R is the resistance per meter long. So if you use in the loop 2, you have additional, right? 2 unknowns. One is the resistance of the RD, the other resistance RC in addition, So this 2 is unknowns, right? So you have to write using more equations. That's not smart, right? So here we're using the loop 1. If you're using loop 2, the equation changed, right? So some students forgot this one. They tried another loops, but ignored right in the load D and load C, right? No D and load C. Okay. Anyway, so you can use in different loops to establish many equations. Here we use in loop 1. Okay. Then we can go to the equations and with the solve it, the solutions. We got the current R1, R2, R3, R4, R6. And next slide will show you that all the current we post positive values. The positive values means that the assumption directions is the same as the true directions. Now, before we go to the next slide, let's have a check about the voltage drops issues. As you see here, as I just said that, suppose the current R1, I2, I3, I4, I5, and 6, the direction is as the same as with assumptions here. Then to see the voltage drops, the voltage drop to A is smaller. The voltage drop to B is smaller than the voltage drop to C, right? So because the voltage drop to the A is 100 meter, and I, so the voltage drop to C, voltage to C, and from this side also the voltage drop to C, so the voltage drop at load C is the maximum values. This is the voltage drop to C from upper side voltage drop to C from lower side so this two is equal. Okay, so the voltage drop to the C from upper side, the voltage drop to C from lower side is equal, actually, is equal, which is the maximum point, right? Which is maximum point. So then we can make the estimations of the cable size based on the voltage drop to the sea. Okay, now we come to the next slide. So as I just said, that based on the 6 equations in previous slide, we can obtain the current distributions I1, I2 to I6. And as you see here, all values be positive. This means that assumptions of directions of the current are the same as the actual. Okay. Then, as I just explained, that the voltage drops to load B is smaller to the voltage drops to load C and smaller than the voltage drop to the C from both sides, upper side and lower side. So the biggest voltage drops points is at C, at load C, which can be estimated with the part 1, 150 meters long, with the current R1, part 2, 200 meters long, with the current I2, and part 3, 250 meters long, with current I3. So R1, R3, R1, I2, R3 from the upper side. Okay, the R here we suppose is the voltage drops per ampere per meter for 2 conductors together. So the current we obtained, the cable length is given, that the total voltage drop to the sea can be estimated like this, with the R as unknown, as variables, right, unknowns. So it said that we should making the total voltage drop from the source to the sea smaller than 2.5% of the source voltage, which is 5 volts. Okay, which is 5 volts. That means these total values should be smaller than 5 volts. From this, we can estimate that the cable's maximum voltage drops per ampere per meter should be smaller than 1.87 millivolts per ampere per meter. Okay. Okay, this is the answers. Now, the things left is that to find out a suitable cables, which the voltage drops per ampere per meter for 2 conductors and environment 30 degrees and installed in a clip stretched in the trench has a voltage drop smaller than these values. Okay. Now, so this how to get these values, from the tables. Okay. Now we share with the tables. Okay. We share my screens. Looking at these tables. Okay, so we have many tables here, but we should find out the 2-core cables, not single core cables. Suppose now we come to this, right? The table A64, which is for multiple armored PVC insulated cables. And for ambient temperatures 30 degrees, conduct operating temperature 70 degrees. It has the current carrying capacity. In this question, the current carrying capacity is not a problem because the maximum current on the cables is about 80 more amperes. So according to the current carrying capacity, so 16 square millimeters cable is enough. Enough. So it doesn't matter. So because the voltage drops has bigger requirements. Now, looking at the current voltage drops. So this is the voltage drop issue. Voltage drops per ampere per meter for 2 conductors we are using a 2-core cable for DC, 2-core cable DC. So the values given here is per ampere per meter for 2 conductor together. Okay, and we just find out that we require a cable which the voltage drop per ampere per meter should be smaller than 0.187 millivolts. Okay. Environment temperature 30 degrees. Now looking at here, so looking at these values, 0.18 millivolts per ampere per meter for 2 conductors. So this cable has a voltage drop per ampere meter smaller than 0.18. Okay. So 0.18 millivolts per ampere per meter, smaller than the 0.187 millivolts per ampere per meter required. Okay. Therefore, therefore we choose these cables. Okay, the cross-section area is 240 square millimeters. That's why we choose these cables. Okay, so in practice, so we have to make sure that the voltage drop on the cables smaller than say 2.5% or 1.5%. So that the voltage from source to the load is within certain values. Within certain values. Okay, so this is the end of these examples. If you still have some questions, you can write to me using the chat box or write to me using the emails after the tutorial sessions. I hope that you have no more questions about the DC systems. Okay, so so that's the end of this tutorial sessions, right? So see you Thursday morning. We will continue to talk about that electromagnetic circuits. And also, you may notice that I just upload exercise on the DC system onto the Blackboard. You may download that questions, try by yourselves. The final answers is attached there, but you can try by yourselves. Whether you can gauge the correct answer there. If necessary, in the coming tutorial sessions, I may explain to you about how you got the answers. Thank you all. Goodbye today.